Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will start with a series of videos about electric potential energy. First, we will understand work in a charged particle. After that, we will introduce electrical potential energy. And finally, we will understand what the configuration of energy of a system with different charged particles really is. So let's start. Right, let's try to understand work for a moving charge. In this case, we're going to have a force in this direction. We can represent it over here. The force that charge 1 exerts on charge 2. And we are going to have a displacement in this direction. Now, we remember that work equals the integral in a path of the force dot product with the displacement. Therefore, we need to understand the different components that this displacement is going to have. Our displacement is going to have two components. The r component in the r hat direction, dr, and a theta component in the theta hat direction. Therefore, when we are doing this dot product, we will need to take that into account. Remember that our force is pointing in the r hat direction, the radially outwards if we take the charge q1 as our origin. Therefore, when we do this dot product, we're going to have an r hat times an r hat, which is going to be a dr, and an r hat times a theta hat, which is 0 because they are perpendicular vectors. Therefore, this is going to be equal to k q1 q2 r squared dr. And now, if we solve this integral, we find along the path z. So this is our solution for the work. Work really is the energy we put into the system or into a charge. When we are moving from one point to another, we need to have our initial and final locations. What we need to see in this case, which is a common misconception, is this negative sign, which is really important. We can also express this by taking the common product in the following way. In this case, therefore, we see that, for example, if the charge is going away, that means final is going to be higher than the initial, and therefore this whole quantity is going to be negative because this will be smaller than this, and we're going to have a positive work because the charge is going to exert that work as outwards is the direction in which naturally the second charge wants to go. However, if we're getting closer, the work is negative because this charge doesn't like the other one to be close, and we need to exert energy into the system, which is what a negative work means, so that they get closer together. Great. Now let's introduce electrical potential energy. If you haven't watched our video from our classical mechanics series in potential energy, you should go watch it now. In that video, we found that work equals minus the change in potential energy. Therefore, in this case, we find that the change in potential energy is K Q1 Q2 R final minus R initial. This change is really the initial potential energy, the final potential energy minus the initial potential energy, which means that we can deduct from this situation that is going to be U final equals K Q1 Q2 over R final. And we can generalize this to the potential energy for a given point, a given distance from other particle is in a similar manner to what we did in our first video on potential energy. We could assume that the initial potential energy was 0 and taking this initial radius to be on the infinity, so that potential energy on the infinity is 0. But it was a really nice form as it was expressing here, and we could easily deduct that it was the best way to do it like this. Now that we have our electric potential energy, there's a whole new world of possibilities open to us in the field of electricity and magnetism. One example of this is understanding what the configuration energy of a system is. If we have a system of charges, the configuration of energy is the energy required to build this system from scratch. So first of all, we would imagine that there's nothing over here and nothing over here, and we just bring this charge from infinity, and that takes us 0 work because really there is no other thing that is interacting with our system, so 0 work to bring our first charge. After that, when we bring our second charge from infinity, we have to do some work because these two charges repel each other. Therefore, we can find that work with or the energy required to do this with our formula for the potential energy. The change in potential energy that happens with charges 1 and 2, it's going to be equal to, we need to specify this distance in this case so that we have a complete expression, and we will say this is R12, this is R13, and this is R23. Therefore, this change in energy is going to be equal to this with the R12 minus 0, because we consider we are bringing this charge from infinity, and therefore the distance will be infinite and also the potential energy over there. So this is our first step. But now we have to bring another charge, which is the third one, once we have the first two. Therefore, we're going to have two more components like this. We're going to have the energy required because of charge 2 and the energy required because of charge 1, which are exactly the same as the first one we found, but for the different charges. Knowing this, we find that the configuration energy, that is the energy required to build this system, is going to be equal to the sum of these three, which is and this is the energy required to build our system. That is all for today. I hope you understood the main concepts we are facing when starting with these energy concepts, but applied to our electricity and magnetism series. If you have some trouble with these energy topics, I recommend you watch different videos we have about it in the classical mechanics series. I hope you understood everything, and any doubts left you may ask them in the comment section and I'll try to answer them the best I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!